If you've coded in Python before, you've probably come across the main Python libraries. Two of the biggest examples, of course, being NumPy and SciPy. These examples are used extensively in the scientific community, and for a good reason. They provide many important functions that are used all the time in scientific research. But compared to what we're about to explore, they're nothing. With the right tools, you can take a simulation of 400 particles and turn it into a simulation of 10,000 particles, but at no extra time cost. The secret, of course, is proper utilization of computer hardware, and more specifically, the GPU, which most people have access to these days. Welcome to the 4th episode of the Python GPU series. Integration. If you guys want to support the channel and learn how to code just like me, I highly recommend checking out my Udemy course, Python STEM Essentials. Coupon code in the description, you can get the course for $10 for the next 5 days. So the main library we'll be looking at today is called torchquad, and so you know that quad, that's the main function you use for integration if you're using something like SciPy. torchquad is basically a library of different integration techniques that was built using PyTorch functionality. And so because PyTorch has GPU accelerated operations, the software is able to take integrals in such a way that GPU is used and speeds up the computations like massively. This is a huge increase in speed we're looking at. So the read the docs page is here, and I also have the GitHub as well. I'll put both links to that in the description. On the side here, you can see the 6 contributors. I haven't met or talked with any of them, but just as a quick shout out, here they are. If you think that this library will be useful after the video, you can go to the GitHub page, you can install it using their instructions, and yeah, let's get to it. Now, of course, the documentation page of torchquad, it has lots of simple examples on how to use the library, and I'll go over a quick example here in the video as well. But the main focus of this video is going to be taking a real-life example of a multi-dimensional integral problem. In this case, it's going to be dropping a magnet through a loop of wire. We'll get to that in a second. And I'm going to compare the speed of torchquad and SciPy for integration. And I'll show you just how advantageous it is to have a library that can perform integration using the GPU. So these are all the packages we need today. Of course, NumPy and PyTorch. I'm going to use SciPy for a little bit of deriving the physics problem as well. We'll use matplotlib for a couple plots. The torchquad function we're going to use today is the Simpson method. I also import this setup backend function that's used to make sure that the GPU is used for the library. From the SciPy library, we're going to compare it to the nquad function, so that has a certain speed to it. That's a CPU-based integration method. This library is going to be used for a little hack. We'll get to that in a sec. And then, of course, the device we're using is going to be CUDA. And then for torchquad, I also set up the backend using PyTorch, so it makes sure to look for the GPU. So what we'll do is we'll start with some basic usage of torchquad and SciPy, just so that we understand how the libraries work. Of course, the main reason why you would use something like torchquad is for high-dimensional integration problems. And so in this case, for example, this very basic example, we have a function of 5 variables. It's the sum of a bunch of signs together. We're integrating them each from 0 to 1. So we have an integral that essentially looks like this. It's just sine of x1 plus sine of x2 plus sine of x3, integrating each of the x's from 0 to 1. And now this is a really nice case because we actually know what the result of this integral is. It's very easy to solve by hand. It's just the ground truth. It's an analytically solvable integral, is 10 sine squared of 1/2. So we can compare. We can take this integral using both libraries and see how long it takes for them to get to this correct answer. And so basically, whether you're using torchquad or SciPy, you need to make sure you set up the integrand function in a certain way. And it turns out to be different in each library. So the way that NumPy works is that, for example, if we're integrating a function that has 5 variables here, this NumPy integrand function needs to take in 5 arguments. So I have this integrand NumPy here, and you can see I'm using a sort of special notation here where I have star x. So by the way, if I define a function f, and I give star x here, and I print x, or let's just return x like this. What this notation essentially does, if I put this star here, is if I give f and I give it like as many arguments as I want, sort of like this, I give it as many numbers as sort of is needed, and I go like this, it will actually return, it will place all of these numbers here into a tuple called x. So for example, x here is a tuple, and I can print the type of x. Let's print the type of x. And this gives me, of course, it will be a tuple. So it takes all the arguments that are sort of given into this function and turns them into a tuple. The advantage of that with the integrand function is I give 5 different arguments of x here. And so this sort of turns it into a tuple of x1, x2, x3, x4, x5. And then it takes the sign of these and it sums them all together. So think about what's happening here. The function takes in 5 arguments and it returns a single number. So all it does is it takes in the 5 different values of xi, it sums them together and returns a single number. And that integrand I can feed into a SciPy function to do regular integration. Now the PyTorch integrand function is a little bit different. It takes in something called x as well, but we have to be careful about what x is. In this case, x is a tensor with shape of n points and n dimensions. So you have to think, well, what does that actually mean? And it will output a tensor of shape n points. So what happens here is that your integration domain, you could think if you're taking an integral sort of discretely, you would sample a bunch of different points for each of the x values, and you take sort of a discrete approximation of the integral. And so you evaluate the integrand at all these different points and you sum them together. And so that's what the n points is here. And so the torchquad function requires that the integrand takes in a tensor where all the points in the integration domain are sort of fed in at the same time. So I have n points and n dimensions, and it's going to output a tensor of shape n points. So in the regular CPU case, it takes in 5 arguments and returns a single number. In this case, it's essentially doing that, but for every single point in the integration domain. So in this case, it takes a PyTorch tensor x, and I want to sum together the dimensions axis, right? Because I have x1, x2, x3, x4, x5, that's the dimensions. The dimensions axis is the first axis, so this would be axis equals 0, axis equals 1 here. And so I sum together this torch.sine x. Remember, this is a 2-dimensional tensor. The dimensions are this dimension and this dimension. And it will sum together the dimensions dimension. I know that's sort of confusing terminology there, but it will sum together this sort of x1, x2, x3, x4, x5. So sum together these signs here, and it will do that for every single point in the integration domain. And so what it's going to return here is it's going to return a tensor of shape n points like that. So I have my 2 integrand functions defined. Then it's really easy to run them now that I have these functions set up properly. So I know that my problem is going to be 5-dimensional because there's 5 different x values. The integration domain is 0 to 1 in each dimension. So it's 0 to 1, 0 to 1, 0 to 1. The ground truth is just 2 times dimension. So in this case, it's 10 times sine squared of 0.5. I don't know why I have it like that. You can just write it like this. So I can define the ground truth. And the true value of this integral is going to be about 2.298. And so now I can get the result using both libraries. So the first thing I'll do is I'll take the result in NumPy. So in this case, I use the n-quad function of SciPy. I feed it in the integrand function, this function here that takes in 5 different arguments, and the corresponding integration domain, which is going to be 0 to 1 in each dimension. So of course, if I just look at this list here, it's just 0 to 1, 0 to 1, 0 to 1, 0 to 1. So it's a very simple domain. I call the n-quad function, and of course, it will return both the value of the integral and an estimate of the error. I grab the first index because that gives the estimate of the integral, of course. So that takes about 15.3 seconds to run. Now I'll do it using PyTorch and torchquad. So this is using the GPU, of course. In this case, you actually have to specify the total number of points you're going to use in the integration domain. In this case, I give 37 to the power of dimension. So what that means is I'm using 37 points in each sort of x dimension. The first thing I do is I initialize the Simpson solver for the integration. So Simpson is the sort of class that I imported here from torchquad. And then I basically just call the integration method of this simp object here. So I integrate the integrand defined for PyTorch, which is this function here. The dimension is, of course, 5-dimensional. This is the total number of points I'm using. And I feed in the integration domain as well. And I can run this, and it runs almost instantaneously. So that, by the way, that was the first time. So the first time you run a PyTorch function, there's a little bit of overhead setting up the GPU. If I run this like over and over, it takes about 0.0 seconds. So it's like basically instantaneously, whereas this takes about 15.3 seconds. And of course, if I print the values of each of the things, they're all getting the same value. So I can actually time this cell as well, just to see how long it takes on average, and compare it to the 15.3 seconds here. So this took 15.3 seconds. This took 47.1 milliseconds on average. So if I just look at the raw time here, you can see that it's about 325 times faster to use torchquad than it is to use SciPy. And so for the rest of this video, I'll look at an actual physical problem where fast integration is basically necessary. So I'm going to spend the next little bit of this video deriving the physics behind this complicated problem. If you're not so much interested in the physics, I'll put a timestamp below. We'll derive the integral, and then I'll come up with a function. It's going to be a 4-dimensional integral that we're going to integrate. So if you're not interested in this derivation, just skip to the next section of this video. So this example is actually based on a real lab I did in the 3rd year of my undergrad. And what happens is you have a magnet, like an iron magnet, and you have a coil of wire. And you drop the magnet through the coil of wire, so it's a closed loop of wire. And what happens is as the magnet falls through, the magnetic field in this coil changes. So if you take the integral of the flux of the magnetic field through that coil, it changes as a function of time as the magnet gets closer and falls through the coil and falls out of the coil. And you can measure that current as a function of time. And by measuring the current through the loop, you can actually get an estimate of the magnetization of the magnet. Now, we'll make this problem a little bit more complicated. It turns out if the magnet falls through the center of the loop, through symmetries and such, you can reduce it to a simple 2-dimensional integral, which can be solved pretty quickly. In this example, we're going to assume that the magnet is falling a little bit off center. What this does is it breaks the symmetries of the problem. By the way, this is the case for most real-world phenomenon. And it'll force us to take a quadruple integral instead of just a regular double integral. So the idea here is that you have a cylindrical bar magnet that sort of looks like this. It's got a total height of L, and it's got a radius of A times L. By the way, you can realize that everything is specified in units of the length of the magnet. It starts at an initial height of H naught times L, and you drop it and it falls with gravity through the loop. The radius is R times L, and the off-center distance is C times L. So we know that the current through the loop is the negative derivative of flux with respect to time. Well, flux is the integral of B dot d sigma. D sigma is an infinitesimal area element on the loop. So I integrate sort of this expression, and that gives me the flux, and I take the negative time derivative of it. Well, I know that the magnetic field here can be expressed as the curl of the magnetic vector potential A. So I can rewrite this integral like this. It's a double integral over a surface of the curl of some vector field. And through Stokes' theorem, you know that if I have an integral that sort of looks like this, I can take this double integral that involves a curl, and I can turn it into a single integral now, where I only need to evaluate this vector field A sort of along the loop here. So rather than integrating over the entire 2-dimensional surface inside the loop, I just integrate along the edge of the loop. That, by the way, will reduce the integral from a 5-dimensional integral to just a 4-dimensional integral. And so then I can also bring this time derivative thing inside the integral. So I have minus dA dt. So all I need to do basically is find the vector potential caused by this magnet at all these different points on the wire. So what we're going to do is we're going to assume the bar magnet has a total magnetization m times z hat. So m is just a little scalar here. And so if we assume that the magnetization is sort of isotropic, so it's the same everywhere inside of the magnet, then it basically has a density of capital M. This is the magnetization volume density of little m divided by the volume of the cylinder times z hat. So this is the magnetization of the magnet. It's a density now everywhere in space on the magnet. We should also specify the points on the magnet and the points on the loop as well. So we know that the position of some point on the current loop is r. It's parameterized by phi. Phi is the angle, of course, on the loop. R of phi is equal to RL cos phi, RL sine phi. Remember, RL is the radius of the loop, and of course the loop is at z equals 0. Now, the position of a point on the bar magnet, well, now we have a 3-dimensional solid magnet. So I need 3 sort of coordinates to specify that. I'm going to use cylindrical coordinates. This is r prime. It's the source point of the magnetic field, so I give it a primed vector. The cylindrical coordinates are going to be r prime, z prime, and phi prime. And then it's basically just equal to r prime cos phi. So that's the x coordinate on the magnet, r prime times sine phi. That's the y coordinate. And the z coordinate is going to be h of t. So h of t is going to be the bottom part of the magnet plus z prime. So I have 3 sort of parameters there that I can get at any point in the cylindrical magnet. And of course, h of t, if the magnet is falling under the influence of gravity, well then h of t is equal to its initial height minus 1/2 gt squared. So of course then I can feed this into this vector and get r prime as a function of time. Now remember that the magnet has a magnetization density capital M. So you can think of it as being consisting of a lot of infinitesimally small magnetic dipoles everywhere sort of on the magnet. And so an infinitesimal contribution, dA, to the magnetic vector potential is dA is equal to mu naught over 4 pi. This is just physical quantities. This is in any sort of electrodynamics textbook. M cross r minus r prime. That's the sort of this vector here minus this vector here, divided by r minus r prime cubed. And d tau is an infinitesimal volume element. And so if I substitute in, of course, this expression for m here, I get the following expression. This is my dA, and it's expressed in terms of d tau. So if I substitute in this expression here for the magnetization density, I get this is my infinitesimal element dA of the vector potential from some point on this cylindrical magnet contributing to some point on the current wire. So my expression for A involves integrating this whole thing here, and then I can feed in that to this expression here. And of course, I need to take the time derivative as well. So if I plug in this expression for A here into the integral above, I get the following integral here where I have to integrate over the loop and then integrate over the magnet. So what does it mean to integrate over the loop? Well, in this case, the loop is parameterized, its position is parameterized by angle phi of the loop here. And so I need to integrate that from 0 to 2 pi. The integral over the magnet, well, that involves integrating over this entire cylinder. So that's from r prime goes from 0 to a times L, which of course is the radius of the cylindrical magnet. Phi prime goes from 0 to 2 pi, and z goes from 0 to L. So these are all sort of the arguments I feed in here. This becomes my integral for the current. Now, in order to make things dimensionless, I'm going to instead solve for what I call I bar equals 4 pi squared L squared over mu naught m times I as a function of what I call T bar here equals root G over L times T. This makes both quantities dimensionless in this case. So I sort of rewrite this integral below, but now I express all the distances in units of L. So for example, now r prime and z prime are going to be dimensionless quantities as opposed to here having units of meters or whatever. And if, for example, r prime is equal to 1, that means that it's equal to L. And if r prime is equal to 2, then it's equal to 2 times L, essentially. And so, by the way, then I can get rid of this sort of L in the integration bounds here. I still have this dimensionless quantity A. And the nice thing here is that dA d tau now refers to this quantity here, rather than having this mu naught over 4 pi, or in this case, mu naught over 4 pi m L cubed A squared, whatever. My dA d tau just refers to this expression here. And of course, dr d phi, well, that's an easy vector derivative to take here. And remember that r now, it's a dimensionless quantity, so we lose the L's sort of here. So rather than derive this whole expression by hand, I'm just going to use SciPy to make it a little bit easier. So all the symbols that I need for this expression, I need capital R, I need phi, r prime, phi prime, z prime, t, h naught, the initial height of the magnet, a, the radius of the magnetic cylinder, r, which is the radius of the wire loop, and c. And c is sort of has to do with the offset of the magnet from the center. I define these all as mathematical symbols here. Of course, you know SciPy. I can type in a symbol here like this and square it, and it returns a symbolic expression for the variables. Then I can define the height as a function of time. Well, that's just equal to h naught minus 1/2 t squared. Remember that everything is dimensionless here. So now I have h. Of course, I can look at h like this, and I get h naught minus t squared over 2. And from there, I can basically get the integrand. So I define my r vector. That corresponds to this expression here. I'll define my r prime vector as well. So r is equal to r cos phi, r sine phi, and 0. My r prime vector, which corresponds to this vector here, that's equal to the little offset here, c, plus r prime cos phi prime, r prime sine phi prime, and h plus z prime. Remember, h is going to be this height as a function of time. My separation vector is going to be r minus r prime. So separation refers to anytime you see r minus r prime, sort of like in this expression here. That separation vector points from the source location on the cylindrical magnet. So there's a small magnetic dipole, that's sort of the source location, and it points to the point on the wire loop that it contributes that sort of magnetic vector potential to. And so my separation vector, if I just look at sort of r minus r prime, of course it can do vector operations here and returns this vector. My magnetization is pointing only in the z direction. And remember that everything is dimensionless here, so I just define it as the unit vector z. You can see that dividing by m here, making everything dimensionless, where capital M used to be, now I just have a z hat here. Then I can define the expression for dAd tau. Remember that dAd tau is equal to this expression here, 1 over a squared, whatever this is. And so dAd tau, I sort of define it like I do above. And so I define dAd tau here like this. So of course I can run all this code and look at dAd tau. And I get this expression here. Of course, that's a function of time. And you'll see that in the integrand above, I need to take the time derivative of this dot product with something else. So I have this vector here. I can then take dr d phi, so that's differentiating the r vector with respect to phi. And then taking the integrand is really simple. I take the derivative of the dot product between dAd tau and dr d phi. So I take this expression and take the time derivative. That's what I'm doing here. And I multiply by r prime. Remember that r prime actually shows up as an additional little factor here, of course, because we're integrating in cylindrical coordinates. And so I can run all this code, and it will define the integrand, and it's going to attempt to simplify the integrand as well, making it a little bit easier to digest. So this is the function here that we want to integrate. And you have to ask, okay, so what exactly is it that we're integrating over? We have lots of different parameters here. Well, like I said above here, we're integrating over phi prime, r prime, phi, and z prime. So there's 4 dimensions here: phi prime, r prime, phi, and z prime. And so we look here at our sort of expression for the integral, where I see r prime, I see phi prime, and I see z prime. But I also see other variables here as well. I see t, for example. So t is a given time, so that current through that loop is going to change as a function of time. I also have the parameter h naught here. Well, h naught is the initial height that you drop the cylinder from. Depending on where you drop the cylinder from, it's going to have a different current as a function of time. I also have the parameter c here, which is the offset from the center of the magnet falling through the current loop. And I also have the parameter a here, which of course corresponds to the radius of the current loop. I also have the parameter c here, which is sort of the offset of the magnet from the center of the current loop. And I have the parameter a here, that's sort of the radius of the cylindrical magnet, and parameter r here, and that's sort of the radius of the actual wire loop itself. So I can solve this integral for different values of t, h naught, a, capital R, and c. There's 9 total parameters here. 4 of them we integrate over, but I can adjust the other parameters to correspond to different physical situations. So like I said, this takes in 9 different arguments here. It takes in r prime, phi prime, z prime, phi, and then the additional arguments t, a, r, c, and h naught. These are additional arguments. So I can convert the SciPy expression to a NumPy function using the SciPy.lambdify. So my integrand function here takes in 9 different arguments. So for example, integrand f, and I give 1, 2, 3, 4, 5, 6, 7, 8, 9. It's just a regular Python function that will return a simple value for that, corresponding to a value of r prime, phi prime, z prime, phi, t, a, r, c, and h naught. So remember that that's a NumPy function. And so this cosine here will be converted into numpy.cosine. But I need a PyTorch function with something like torch.cosine if I'm going to use the torchquad library. So there's not really a simple way to convert a NumPy function to a PyTorch function. The way I do this is using the inspect library. So basically what this does is it takes all the code for the integrand f function. This will basically return a string. And so that's a string of all the code in that function. I replace cosine with torch.cosine and sine with torch.sine. And then the function name is called lambda generated. So by the way, if I just look at this here, it'll be a string. And it defines this underscore lambda generated function here that takes in all these arguments. I want to replace this name here with integrand f pytorch. And then it executes this entire function. So it executes this string of code. So this gets replaced with integrand f pytorch, and it will run that string as if it's running code. So by running this cell, even though I don't define integrand f pytorch, it executes that string of code, and I actually have this function here that has sort of torch.cosine and torch.sine instead of regular cos and sine here. So now we write a function to solve the integral for a given value of time, a, h naught, r, and c using the torchquad library. And what I'm going to use is I'm going to use 37 to the power of 4 points. What that means is 37 points in each of the 4 different dimensions. Remember that the integral we're taking is 4-dimensional. So I start by creating this Simpson solver. So I'm matching the integration domain as follows. Remember, like, the order of the arguments here. So r prime goes from 0 to a, phi prime goes from 0 to 2 pi, z prime goes from 0 to 1, phi goes from 0 to 2 pi. So then I actually create this integrand function here like this. Remember that torchquad requires taking a single tensor as input. So it takes in the single tensor d, and it returns the integrand f PyTorch function by feeding in each of the corresponding dimensions in the appropriate sort of argument here. So remember that, like I said above, the dimensions of the torch tensor is n points times n dimensions. So the dimension axis, of course, this is a quadruple integral, so there's 4 different dimensions to this integral. The arguments are going to be this axis here. So this is the first dimension, second, third, and fourth dimension. And then it also takes in all these additional arguments here. So t, a, r, c, and h naught. So now I have this thing called integrand, which is really a function that takes in a PyTorch tensor. I give this to the simp.integrate method, this integrand. It's a 4-dimensional integral. The number of points I'm using is n, and the integration domain here is going to be this domain. But what I really want to do is I want to solve the current as a function of time for given parameters a, h naught, r, and c. So I have a certain magnet of a certain volume and configuration. It's offset from the center, and I drop it, and I solve for the current as a function of time. Well, then I sort of derive this solve multi-times function. So this takes in an array of times here, same arguments here, and it solves for the current as a function of time. So basically using a for loop, it's going to solve the integral for each value of time separately and put them back into a PyTorch tensor. So we'll try this for 2 different cases, by the way. So what we're going to do is we're going to try it for the case where c equals 0, so the magnet is falling through the center. And we'll also try it for c equals 0.1, so the magnet is slightly offset from the center. And you might wonder, well, what's the difference between the maximum current in each case? For example, if I displace that magnet a bit from the center and let it fall through the loop, will I get a larger maximum current? And that's something that you can't really look at this integral and solve directly. You can set up an experiment where you drop the magnet from different points and measure the current as a function of time and see, well, what's the maximum current based on where I drop this magnet off-centered in the loop. Or you could set up sort of this simulation that we're doing here with the integral. So we'll have c is equal to 0 and c equals 0.1 times L. So we're going to solve for 500 different times between 0 and 4 seconds. Remember what's happening here. We're taking 500 different integrals. And so this is why it's so fast to use something like torchquad, where taking 500 integrals, if they take 15 seconds each, you're looking at a very long time for something like SciPy. So we'll have 500 different times, and we're going to use the solve multi-times function for the value of t. We're going to set a equals 0.1. So a is the radius of the cylindrical magnet. H naught equals 1. R equals 1. So that means that the radius of the loop of wire is the same as the length of the magnet. In this case, we'll have c equals 0.0, and actually I have c equals 0.25. So I'll actually sort of solve it like that. So I'll sort of solve for the current in 2 different cases. You can see, by the way, that it solves very fast, only 5.7 seconds to solve basically 1,000 different integrals because we're doing it 2 different times. And so now we can plot the current through the loop as a function of time. So remember that the current and the time are dimensionless quantities. So on my axis labels here, I have sort of this proportionality factor times I, this is dimensionless, and this quantity here, g over L times t, is dimensionless here. And you can see that, by the way, that if I drop my magnet, if I off-center the magnet through the center of the current loop, I actually get more current through the wire. I get a greater maximum current in each case. Of course, you can see that, okay, it goes to about -20 here, and then up to 30 here. Well, that's, of course, because the magnet is gaining speed as it falls through the loop of wire. So the magnetic field changes more rapidly as the magnet is moving faster. So now what we'll do is we'll solve it using SciPy's n-quad function, and we'll compare the times that these things take. So these are the corresponding ways to solve the integral using sort of, I call it NumPy, really it's SciPy, but it's basically the standard way of solving integrals in Python. It's basically the same as the functions above. It takes in the time and the parameters here, and it will call the n-quad function to take the integral. And then this function here will take that integral at many different times. And so in this case, because it takes so long, I'm only going to solve for 10 different values between 0 and 4 seconds. And so we'll let this run. All right, so this code took about 30 seconds to run. And now we're using only 10 points as opposed to 500 points as well. And I think this final plot really shows why you might want to use a GPU for taking integrals very fast for problems like this. So here we can sort of compare between the data that we obtained using sort of CPU functionality and the massively greater amount of data we obtained using the GPU functionality. And so here, these black points that took 30 seconds to run, by the way, are from the CPU. So this is sort of the amount of data you can get in 30 seconds from the CPU. Whereas using the GPU, it took only about 2.5 seconds to get this blue curve. So we get a smooth curve, much more data, many, many times faster. So that ends it for this video. Congratulations on making it to the end. I know it was a very long one. If you're interested in using the software, again, be sure to check out torchquad, both to read the docs and the GitHub. There's a link in the description below. Join the Discord server, like and subscribe, and I'll see you next time.